Nadimpalli of IIT Kanpur, and he's going to talk about the uniqueness of branching to fixed point subalgebra. Santosh, please.
Thank you for giving me this opportunity. And yeah. So, okay. So what we let's start. So let G mathfrak G be complex semisimple Lie algebra. Okay. So now let theta be an automorphism of G as Lie algebras, and theta power n is identity for some. Okay. So we assume that, and now G0 is the stabilizer of G. So G theta for x inside G, so theta x is x. So G0 is Lie subalgebra. So we got G Lie subalgebra. So yeah. So this we know very well, and examples you can get many examples. For example, G is say GLV or GLN. Okay, complex semisimple. So SLN, and you can get all classical Lie algebras as G0. We all know this very well. So yeah, another interesting example could be just G is G0 direct product G0, say n times, and theta of x1 up to xn is xn, say x1, etc., xn minus 1, the cyclic permutation of the coordinates. And we can do something more crazy or rather more interesting, is that let theta be, say you fix an automorphism of your yeah, I mean this. Okay, so fix an automorphism of your Lie algebra. G0 is again semi-simple complex Lie algebra. And then you can also define, say, theta 0. Say you can define theta, so take G to be G0 times G0, say n times. And you can take theta of x1 up to xn to be theta 0 xn x1 up to xn minus 1.
So, Santosh?
Yeah.
This G0 is always a fixed point subalgebra you had taken earlier, or it is any semi-simple algebra?
Okay, so maybe it's notational conflict. So let's say just fix some T. Okay. T is not total, just T is any semi-simple Lie algebra. Okay, just assume simple.
So in example C, I guess theta 0 is of order n, the same n, I suppose.
Right.
Yeah.
Yeah.
And these are always Dinkin diagram automorphisms. Is that something that is?
Yeah, I'll come back to
okay.
that during the talk. We can always reduce it to these three prototypical examples. That's the usual case. So that's why I want to right away start with them. So you take this guy, okay, and of course G0 is going to be the diagonal embedding of T fixed points by theta 0. So sometimes I denote T theta 0 or G theta for fixed points algebra. Okay, so okay. So for instance, for example, if n is 2 and say G is SLN and say theta is minus x transpose or something, then we can see that G0 is the diagonal embedding of two copies of SO or the corresponding thing inside SLN cross SLN. Okay.
Sorry, and in the example C, you made theta naught is an automorphism of T, right?
Right.
Yeah, thanks.
Thank you.
And what Ambri asked is everything of the Dinkin diagram automorphism. That is, these are the outer ones, right? I mean, there is also the inner.
outer ones. Yeah. For the present problem, it doesn't matter. So I will go to that during the discussion.
Yeah, thanks.
Right. So these are some examples. Usually prototypical examples that I have in mind, but the general case we will address soon. Okay, so the question is this. Question is if V1 and V2 are two irreducible finite dimensional representations of G, then you ask when or characterize the pairs, let's say, then when do we have restriction to G0 of V1 isomorphic to restriction G0 of V2. Okay, so this is a question. This is a problem I want to talk about. Okay, so if you go to example B, so in example B, that is G0 is the diagonal embedding of T inside T cross T, and T is simple. So this goes back, the answer goes back to work of Rajan and Venkatesh and Vishwanath. Okay, so I guess the order of alphabetical order is right. So this is so this goes back to work of Vishwanath and Rajan. Their usual statement looks like if V1 tensor Vn is isomorphic to W1 up to Wn, where Vi and Wi, Wj are irreducible finite dimensional reps of G, then the set containing V1 up to, or let's say there exists a permutation sigma inside, then okay. Then N is M, and there exists sigma automorphism Sn such that so Vi is isomorphic to W sigma of I. Okay.
Remove trivial factors also, right?
Yeah, probably you exclude that case, right?
Yeah, I would think you probably, I don't know. Should we say something like none of them is one dimensional or something?
Yeah, let's say non-trivial irreducible. Not one-dimensional case, right? So that sort of thing can be formulated by saying that if this I think of this as something like, I mean, of course. So if so you can think of this V. So take V to be, so now any irreducible, so take G to be this guy as usual, T, and any irreducible of G is of the form V1 tensor Vk. Okay, so now I will assume that yeah, so I'll take two representations. Say V is V1 tensor up to Vk or Vn, and W is some W1 tensor Wm. Then the problem says that so restriction to G0 of V is isomorphic to restriction to G0 W if and only if there exists a sigma in the outer automorphisms of G such that V is isomorphic to W twisted by the sigma, right? So this is what the statement looks like. Now, well, so if you think about it, so if you consider T cross T as the complex semisimple Lie algebra, then the outer automorphisms, so fix a Borel, fix all the bad guys, Borel, B, Cartan, T, so Cartan H of T, and of course we get the
Hi, why is the if part true?
which one?
The if part, if and only if sigma belongs to outer
Because
automorphism.
sigma fixes the diagonal, right? Sigma fixes the diagonal, no? So we are trying, G0 is the diagonal embedding of T.
Okay.
So sigma.
No, why is the restriction isomorphic for any other outer automorphism?
Okay, I think the confusion is that there. Okay, so maybe I should say there exists. Okay, let's not say the other way. In fact, that's what I was trying to address.
Okay.
There exists a sigma in the outer automorphism. Okay, let's. Thanks for pointing.
Thanks.
Okay, so now, so if you fix a Borel subgroup B, Cartan H of T, of course, you get something for G itself, the product of the things. And now we can talk about go into that detail. But outer automorphisms of G are not going, this is of course going to be larger than the coordinate permutations, right? So it's larger than Sn considered as coordinate permutations. So in Rajan Venkatesh Vishwanath's work, you get so you get the subgroup of, so this sigma is contained inside the coordinate permutations of Sn, right? So that means that if we want to formulate a statement, the general statement, somehow these automorphisms have to also be fixed. Like we have to define the relevant automorphisms of the branching problem. Okay, so that is what we try to do. And okay, so let me go further and discuss another example. So the another example of interest, or rather the problem started, I started thinking about this, is that of G is simple of the form say D4. Okay, and we have theta as a triality automorphism. So you got D4. So alpha 1, alpha 2, alpha 3, alpha 4. So you got triality automorphism theta, which is the cyclic permutation of these three roots. Now, so yeah, so G0 is going to be a simple Lie algebra of the form G2 type. So you can also look at the Cartan subalgebra H0 or G0, H0 is spanned by beta 1 and beta 2, where beta 2 is alpha 2 itself, and beta 1 is alpha 1 plus alpha 3 plus alpha 4 by 2 by 3. I mean, yeah, doesn't matter which scalar. So you can see that H0 is now fixed by the entire set of outer automorphisms of D4, right? So this is going to be S6, so I mean S3, so a group of order 3, and it's going to be fixed by all outer automorphisms of D4. Okay, so therefore now we get that if V is an irreducible representation of D4, then irreducible, finite dimensional, etc. Then, well, yeah, okay, any representation, okay, irreducible, finite dimensional representation of D4, then we get that V is isomorphic to V sigma on restriction to G0, right? So then we also easily showed the converse of this statement. Okay, so if V and W are finite dimensional irreducible representations of D4, then V is isomorphic to W if and only if there exists sigma in the outer automorphisms of D4 such that V is isomorphic to W twisted by the sigma. Okay, so this is slightly different from the case of the diagonal embedding of product of simple Lie algebras. There you don't get the full outer automorphism group, but you get a restricted outer automorphism group. Okay, so these sort of examples will lead us to the main statement of what we expect at least, and what we proved. I will also explain. Okay, so yeah, so let's get back to the case of So let's start with the general case. So let G be, as usual, semi-simple complex Lie algebra, and theta inside outer automorphism of G with theta power n is identity. Okay. Now, well, you can actually, this is a result of Steinberg in his book on endomorphism of, yeah, for the famous lecture notes, we start as endomorphism. You can show that there exists a Borel subgroup, Borel subalgebra, B and Cartan H, such that so theta is inside the automorphisms of G, which fix this Borel and H. Okay, so yeah, this also can be just proved by showing that well, and also if you take H, you can also show that G0 is going to be reductive, and if H0 is inside G0 is Cartan, then the centralizer, so G centralizer of H is H0 is a Cartan for G. Okay, so probably a reference for this is Cass's book on infinite dimensional Lie algebras. There he assumes G to be simple, but you don't need that. Okay. In fact, in original work of Kaas, he proves it for semisimple complex Lie algebras.
Here, this Cartan is your H here, where theta belongs to R automorphism GBH, right?
So there exists one, but this H has nothing to do with this statement.
Need not be same?
Well, you can get the same. Yeah. So this result implies this as well. Because you can show that there exists a regular element in H0, and if you take its centralizer, it got to have H. So that is stable under theta.
So you, in this H, you take that H, right? Theta belongs to that.
One can take it, yes. So this lower statement implies the above statement, but as it is, they are independent. Okay. So yeah, so now you can write your theta as, say, some iota times composite theta 0, where iota is some inner automorphisms of G, and theta 0 is in the outer automorphisms of this B, H, and probably fix a Chevalier pinning. Okay. So fix some mapping lash and pinning, so you get theta is in the outer automorphism. Okay, so now if you want to understand, say V and W are two irreducible finite dimensional representations of G. So you got G0, which is the fixed points of theta. So be careful, this theta and theta 0 here. So now you get that restriction of G0, V is isomorphic to restriction G0 of W. So you can get that. So this if and only if, so restriction to G theta 0 of V is isomorphic to restriction G theta 0 of W. Okay, because inner automorphism is going to preserve your H, and so the wild character formula will immediately just give you this. Okay, so you can reduce your problem to the outer automorphism case. Okay, so this hence we can just restrict to the case of outer automorphisms.
Sorry, Santosh, can you recall theta naught? What is theta naught here?
So I just write theta as iota times theta 0, where theta 0 is the outer automorphism after fixing all the usual data, but the pinning of the complex semisimple algebra.
This X alpha denotes what? What is this X alpha?
This is a Chevalier pinning. So
okay.
So I mean, just the usual thing. There's nothing. So okay. So yeah. So from now onwards, we assume that we assume that theta 0 is in the outer automorphism group of G with B, H, and X alphas. So I'm just using the usual root system fee, the usual notation of Bourbaki kind of thing. Okay, so you get this theta 0, and yes, so then well, let's not be a safe conjecture, but am I audible?
Yeah,
okay,
I can hear.
Okay, I thought I lost. So conjecture or wishful thinking. So we define. So we say set H0 to be H fixed point by this theta 0. Okay, so this is contained inside G0 Cartan. Okay, And now we take the centralizer of this H, which should be your H itself. Okay. So, yeah. Now let's define H theta to be set of all automorphisms sigma inside the automorphism G, B, H, X alpha, such that sigma of X is X for all X inside H0. Okay. So if you define this group, then, well, let's say wishful thinking, after several computations using using software, which is Sage software, so we concluded that this statement must happen for the following things. So if G is a complex semisimple algebra, okay, and if G, so we can write G as product over, say, delta, where delta is a Dynkin diagram. Say G delta. Now G delta is the isotypic component, is the, well, kind of isotypic, is the largest ideal, well, with simple factors of the type delta, and we assume that G delta, when delta is of the type A to N, has length 1. Okay, so somehow the philosophy being that so you can obtain all classical root systems from folding of An, right? So, but the point is that for A to N, there is some problem. So because you got two things in the Dynkin diagram, in the middle, we got two things, not just one thing. So somehow we get counter examples for what we are going to write in that case. Okay, so now if you have this, then we think that if V and W are irreducible representations of G, such that restriction to G0 of V is isomorphic to restriction G0 of W, then there exists a sigma inside this H theta such that V is isomorphic to W twisted by the sigma. Okay, so this conforms with most of the examples that I have given. So we will also prove okay. There is some so we will so this is what we expect, and what we prove we could show is that if the same continuing the same hypothesis,
sorry, Santosh, when you say length 1, you assume there is only one factor, A to N, only one factor.
Yeah, A to N, only one factor. I mean, probably one can do much better, but it doesn't look very neat compared to what the statement I'm going to write. I mean, the statement, the wishful thinking conjecture, it looks very very nice to write, but A to N case, the counter example, I don't understand it, so I don't know how to characterize them or something. So that's why I assume that. Okay. So what we could prove is that when length of G delta is less than or equal to 2, then we could show this. Without any assumptions on V and W. Okay, but we can also do much better. So with certain generic hypothesis on V and W, which I will explain, we can show the general, let's say, let's give it a name, say general conjecture. So the point is that now let's say since we have, what are these hypotheses, right? So now we have fixed B, H, and these data. So of course we can talk about dominant weights with respect to them, to this thing, these data. So now whenever you have a folding root, then I assume, so you have this G delta, and of course theta fixes this ideal. So you can look at the folding roots, right? So delta is, say, disjoint union delta 1, delta 2, etc., delta n. So look at alpha in delta I, such that alpha is fixed by all automorphisms of delta I. Okay, now you can, if lambda and mu are two highest weights, then I assume that the lambda comma, say, so let's say this is alpha I. So the minimum max of this, so alpha I is folding in delta I if this is less than equal to all the other roots. Okay, so lambda comma alpha inside P, and alpha is not folding. So it's like if the folding roots, if the values of lambda at the folding roots is very small in comparison with the value of lambda at other roots, then we can actually show this theorem. But unfortunately, in general, we can't show the result, but we still could not find any counterexample except for the case of A to N, in which case you have abundance of counterexamples. It's very easy to write. Okay, so let's get back to maybe the proof of, or how do we prove this theorem, right? So
what do you mean by folding root?
So folding root, take any Dinkin diagram. So you're looking at those roots which are fixed by all outer automorphisms of the Dinkin diagram.
Fixed to, okay.
Yeah, it is like, yeah, we also assume it's simply less, right? So otherwise theta will be trivial, and then
Yeah.
Okay, so
can I ask one question? So
yeah.
For H, you are fixing H not element wise, right?
Yes.
So when So isn't it a stronger condition than just fixing H naught? Like when you're
No. This is the right object to look. For example, if you don't fix this, then you have lot more elements in the outer automorphism. So yeah, so you need this. Yeah. So for example, I think if you work out what happens in the case of diagonal embedding, in the Rajan's case, if you don't ask for pointwise fixing of this H0, then you'll get much more elements.
So, but then in your, like when you state your theorem, right, you're saying then sigma belongs to H theta. So if you allow all of that, then that gives you a bigger set. I mean, is the result true for that bigger set? Right?
Yeah.
I'm asking, so you have stated your result that, I mean, there exists sigma in H theta such that V is isomorphic to W sigma, right? So
Right.
for the cases that you have done, I mean, that is there. For the cases where you are not able to do,
Yeah.
in that case, you don't take H theta, but you take all such that just fix H naught. Will it be true in that, like take a bigger set? Now you have a...
No, the cases we couldn't do, it's not because the statement is false. It is true, but we can't prove this.
Okay.
I mean, how can you say something is true without proving? But I mean, it's not. We have tried a lot to do find counter examples on Sage or Lee software, but we couldn't find.
Okay.
So your experiment suggests that this is the correct proof. You don't need bigger than this. That's what.
Yeah. So H theta is what is required. Yeah. And already if you, yeah. Okay. So let's go to the...
For the A2 case also, this full outer automorphisms will also not suffice, right?
Yeah, A2N case. Yeah.
Won't suffice. Okay.
A2 case is too small. That is the problem. You can get a lot of counter examples.
So in that case, I'm saying like if you put more things like outside H theta also, you cannot do it.
I don't think that matters so much because you see H theta is either it's fixing pointwise H0 or not. I mean, you won't get many automorphisms, right? Ultimately, you're going to get finitely many automorphisms. But we have infinite families of such counter examples. So we can't explain them using this thing. Like,
okay.
Yeah. So I don't know what happens in A2N. Probably I should shut up. So sorry for that. I could not characterize, and yeah, it would be good if someone comes up with a modification. So
Thanks.
yeah, so the method of proof is so okay. Maybe I should. Are there any questions? Okay, yeah. Method of proof. So method of proof is very similar to Rajan's case. So you basically look at the character while character. So while character. So basically, let's say lambda is in P, where P is the weight lattice of G. Okay. Now let's say you got CH lambda is a character of V lambda, irreducible highest weight representation of G with highest weight lambda, right? So now this CH lambda is going to be summation W inside the while group e to the power W lambda plus rho by summation W inside W e to the power W rho. So now, yeah, so it's very easy to just argue. We can read. So suppose we look at V is an irreducible V and W are irreducible representations of G delta, fix some delta, okay, the Dinkin diagram. And also you can assume that, so say if you write delta is delta 1 up to delta K, disjoint union, you can assume that your theta sort of, theta, the cycle of theta on these delta 1 up to delta K is unique. So theta acts transitively on these sets, delta 1 up to delta K. Okay, so theta takes the cycle, there is this unique, there is exactly one cycle of theta on delta 1 up to delta K. Okay, so you can assume these things, and let's say you have V is V lambda 1 tensor V lambda K, and W is W mu 1 tensor W mu K. Now you got a map from, say, P0 is the weight lattice or G0 with respect to H0. Then you got the projection map from H star to H0 star. Of course, this will take ZP to ZP0. So now you can consider CH lambda 1 to CH lambda n lambda K, P of this guy. We are given that, say, this guy is P of W mu 1 to CH mu 1 up to CH mu K. You can reduce you can show that this is if and only if, so P of, say, U lambda 1 up to U lambda K is P of U mu 1 up to U mu K, where U of lambda is the well numerator or normalized well numerator, let's say. So e to the power is equal to summation e to the power W inside W lambda plus rho minus summation W inside W e to the power W lambda plus rho minus lambda plus rho. So you can just do this. And now we have to expand each of these U lambda. So we use Rajan's technique of expanding U lambda at some root. Okay, so now you can U lambda, you can consider this is as a polynomial.
Sign is missing. Okay. U lambda.
Can you repeat what you said?
U lambda has sign, summation, well numerator. Sign of W.
Oh, sorry. I mean, yeah. Sorry for that. Thanks. Yeah. So U lambda, you can consider it's a polynomial in terms of these symbols e to the power minus alpha. So alpha inside the simple roots, delta, right? So now you basically, so if I set x alpha is e to the power minus alpha, like these are all notations probably I have stolen from Venkatesh and Vishwanath. So thanks for them. So you look at this guy. So now you basically expand U lambda as a polynomial, in some alpha. Okay, so the ideal thing to do is that, so you basically now we need to choose which alpha we would like to expand this, right? So Now we'll have this G delta, and this contains G0. We identify G0 as the diagonal embedding. So so we have G0. Say G delta is equal to T cross T some K times or N times. And you have G0 to be T of some automorphism. Okay, it need not be theta 0 itself, but it's some automorphism. So yeah, so I just denote by T0, where T0 is some automorphism, fixed point subalgebra of some automorphism out of T0. Okay, so of course these automorphism can be determined completely based on what your theta is doing on these factors. Okay, that's not so it makes no sense perhaps to precisely pin down that thing. So you have your theta permuting these factors, and G0 is something like this. And now the main point is that this alpha will expand this u lambda at the folding roots of alpha, right? For example, if your Dinkin system is say E6 or something, then you got so we expand here, right? We expand along this guy. Okay, so you expand this u lambda as a polynomial in X alpha. Okay, expand as polynomial in X alpha. So this will be so you some lambda prime. So this will be a polynomial in X beta, where beta is not equal to alpha. And in fact, you can write the lambda prime some highest weight. This is the representation highest weight for this whatever is left, right? The Levy subgroup K. Okay, so this is the representation. So this is a well numerator of some Levy subgroup, which is delta corresponding to the simple root delta minus alpha. Okay, so you get this guy plus X alpha raised to the power, you get lambda plus rho comma alpha some u lambda double prime. Of course, this lambda double prime is also some highest weight for delta minus alpha. Okay, plus dot dot dot. Okay, now of course now you have to take P map P. So u of alpha u lambda will be P of u lambda prime plus X alpha is fixed, so therefore P is not going to touch it. So you got X alpha lambda plus rho comma alpha P of u double prime plus dot dot dot. Okay, so now you take the huge product over all these guys. So let's say we set P of u lambda is a small u lambda, and then you get that product over u lambda prime plus u lambda double X alpha lambda I plus rho comma alpha. So you got I as well here, u lambda double prime plus dot dot dot. So is equal to the similar thing on the other side, right? So this is what we have. So this formula is obtained by just expanding these two things. Now, so Rajan's case, it turned out that if you look at sums of the form, so summation, so if you look at the terms u lambda double prime by u lambda prime, so this set lambda, so lambda, and well, you can just take any lambdas over lambda ranging over some finite set in T, then this is linearly independent. So basically, he could immediately use this fact to show the uniqueness of tensor product decomposition. Okay, but it turns out that in our case, in the general case, where, for example, so this is not true. This is not true. So what we needed to assume is that these, one immediate, either you assume that this product is just over two factors, or you assume that these guys are going to be distinct for each lambda I. Okay, so you assume that these factors are large compared to the other coefficients, then you can use elementary symmetric polynomials in terms of these guys to still prove the equality, still prove the uniqueness of this tensor product decomposition. Or otherwise, you have to assume that this is exactly two factors, in which case you can straightforwardly prove it. Okay, but in general, so we couldn't handle the combinatorics of expanding beyond the first coefficient. So the second coefficient onwards becomes very complicated. So I'm not, so I couldn't handle the combinatorics. So we just proved in these two cases. Okay. So yeah, so that is how the proof goes. And okay, maybe I just stop here. So are there any questions? Maybe based on that, we can go ahead.
I don't have a question, but I have a kind of thought. So you're looking at the restriction from G to G0. And one common way of studying these restriction problems is to try to look at some sort of adjoint functor, which is an induction.
Yes.
And this problem that you have stated about two isomorphic representations, whether they should have isomorphic restrictions, can be rephrased in terms of induction. And I think it might be saying something like, the image of induction spans all irreducible characters, forms the basis of irreducible characters. That is, the induced things are enough to get all the representations of the big Lie algebra.
Like ARCSIN's theorem, fine, true.
So I was wondering if this kind of an approach could also be applied to this problem.
Okay, I haven't thought in this.
Maybe Vishwanath has thoughts about this or something.
I was just wondering, wouldn't it become infinite dimensional? See, it's like you'll have to induce from the induction is like universal mapping algebra of the bigger guy tensor
You
over
have to get the right notion of induction, which is a left adjoint to this restriction, or right adjoint, anyway, which is adjoint to this restriction.
Something like that, I think so. For example, someone already studied this using, so I think there's already some work who already made somewhat similar conjecture like this. They have proved it for maximal Levy subgroups of classical groups. So there is some paper in Glasgow Journal of Math, I think, sometime. So some people have already considered this, but I never thought of this from ARCSIN's theorem perspective, like characters. But somehow we are fixing one G0. Like if you vary G.
Yeah, no, you fix one G0, and then this thing should mean that when you induce from this just one G0, you'll get enough characters to span everything. Whatever that induction means, since I don't really work with Lie algebras usually, I'm not sure exactly how that should be done, but there should be some.
something like this, I think, but I don't remember what.
I don't know what the functor is exactly. It's just a thought. I mean, it may not be valid, of course. Needs to thought maybe. Any other questions?
I have one. I mean,
Yeah.
sort of. So you have given, I mean, going to Rajan's problem and Rajan Venkatesh Vishwanath problem. So this is the restriction is isomorphism. So instead of that, if I just want to know that in the restriction has certain multiplicity, may not be isomorphic. Is there anything else that we can say in that case?
That's not true. We found counterexamples to that fact. So if multiplities are the same, you're trying to say that if constituents are the same, then perhaps the tensor product is the same, right?
Yes, some constituents may not. I mean, yeah, this is not an isomorphism at the restriction level, but there is a non-trivial intertwiner.
I think we have found some counterexamples. I think when working with some maximal subgroups, I think restriction to maximal subgroups, we can find that multiplicities. You can find that constituents are the same, however, the multiplicities matter. So the representation, you can't get unique factorization with just multiplicities. This is like eigencone problem, for example, right? So, for example, what you are roughly saying is that suppose you know saturation, and then it's like saying somehow the inequalities of the eigencone determine lambda itself. So what can happen is that your eigencone, I mean, can be like some convex body given by some rational hyperplanes. You may not capture your lambda, the integral point, right inside it. So I think some such phenomena was happening. I don't remember the exact detail. Been some time, but just you need also multiplicities. That's not true. If you exclude multiplicities, probably it's not true. But I don't know the general statement, what is expected. For example, when you do SL2 proof, you don't use any multiplicity. You just use PRV component to say something. Yeah.
This is still what you're answering is in case all the constituents are same. So if I don't even put that condition, so if I just say that, I mean, that's like a very weak question really, that I just want some constituent to be same. Is there something that I must have at the top? Like, is there any thing to be expected in that case? I just want one constituent should be same in the restriction, at least one. Will there be?
Yeah, so the highest thing and lowest thing can be characterized some Casimir kind of characterization for the highest PRV, I think. Rajan says that other things cannot be characterized. So I don't know what should be expected, but something like if you V lambda mu1 plus mu2 must occur with multiplicity 1 in V mu1 tensor V mu2. This is almost trivial, right? So that should be the same. Some things are to be there, like, I mean, but in between, some don't know.
I think my audio is a little bit problematic. Yeah.
Okay.
We can hear you.
I couldn't hear. Okay, it's okay. I couldn't hear in between.
So I mean to say that the highest PRV component, or what if this is called highest PRV at all? I mean, anyway, this component must occur inside this with multiple.
As well as in the other one. Then only there will be a component.
So you can say that sum of mu i's must be the same as sum of lambda i's.
Okay. Okay.
And beyond that, I don't think I'm not. Probably mu1 minus mu2 also you can say is lambda 1 minus lambda 2. Yeah. So yeah, this is not my traditional area of research, but just out of curiosity. So thanks for listening.
So any more questions?
I can ask one more question, more of
yes.
maybe theory. So what will be the analog of these? I mean, if I take any group, right, you can take an automorphism and you can take a subgroup like G0 that you have. Are there any questions in that direction ever, like in certain classes of groups? Is there anything like that?
I asked Dipendra this question. He said that he expects it to be true for cuspidal representations of finite groups of Lie type.
Oh, can you say it once more? I couldn't hear. I think there was.
So he gave some example. I mean, some numerology kind of immediately says that if you take finite groups of Lie type of rank 1, let's say, then if you take product of two cuspidals, then it has to be unique.
Oh, is that okay? Okay.
But obviously, you can't expect that for principal series. I mean, it's almost collapses.
Uh-huh.
Yeah. So actually, the interest for this is about Langland's parameters in terms of what I call converse theorem.
Okay. Okay. Thanks.
What?
I'll hear the whole thing. I'll come back to you, and I think I'll
Yeah, I
come to you.
think that statement about cuspidal sounds very interesting, right? I mean,
Yeah, but that happens
exactly.
for GL2 or for
Exactly.
rank 1 cases, it happens just because, you know, all of them are same dimension, like you can literally match them. So P minus 1 by 2 square must be sum of the principal series or yeah, so you can, that really matches well. So I forgot that sometimes, but right. Yeah, so P minus 1 square, the dimension of cuspidal. I think this must be sum of all cuspidals or something.
One has the decompositions.
It has
You
two,
don't.
it breaks into two cuspidals, I think. So two cuspidals plus the regular representation or what this thing. Sorry for, yeah, maybe I can get that. Yeah, this must be some kind of an exercise. Like, you know the dimensions very well, so you have no other choice.
And this is only for two cuspidals. So is there something that one can do with, like, if I take n cuspidals, there is, I mean, parallel.
I don't know. Sorry.
Like, I mean, here it's like a general, right? You can take any number of terms and still result of this nature is true. Yes?
Yeah, I don't know. I will later discuss. Sorry for that. I don't. The point is that, yeah, I don't have a lot of intuition for product of three cuspidals.
Okay. Okay. Thanks. Thanks. Yeah, I'll check with you more details.
Yeah.
Thanks.
okay. So, any more questions? So I guess if there are no more questions, let's thank Santosh for this really beautiful lecture. Very nice. You can unmute your mics and thank him.